Okay, so the next speaker is also needs no introduction, but I will introduce him, Subhasish Mitra from Stanford, that will continue the line of talk from the previous talk, and we'll talk about the future of hardware technologies, I guess more for the three-dimensional aspects of that.
Thank you very much. It's really an honor to speak at this event. And I will talk about the future of hardware technologies for computing. But before I start my presentation, I would like to thank the students and the collaborators and, of course, the sponsors that made this work possible. So I would like to go way back. And if you look at the early days of computing, those were dominated by implementations using electromechanical relays, vacuum tubes, discrete transistors, and then the modern-day integrated circuits were born. As you all know, that Jack Kilby got the Nobel Prize in 2000 for integrated circuits. And I would strongly encourage you to read the Nobel lecture by Kilby, because you would see that whatever was going on in the 1950s, at that time is very similar to kind of what's going on today. That sort of gave birth to integrated circuits. Anyway, so Kilby in his Nobel lecture talks about this birth of integrated circuits. People at that time literally were taking discrete transistors, and they were actually trying to even put discrete transistors on top of each other, which would be like what Professor Patterson talked about through silicon vias. That kind of reminds me of those things. Anyway, so when Kilby built the integrated circuits, he talks about that there were three big complaints about integrated circuits. The first one was that the yields, which is what's the chance that the chip would actually work. The yields would always be too low to be profitable. That was the first complaint. The second one, what he was meaning is that the best transistors at that time were not built with the kinds of materials that we use in integrated circuits today. But I love the last one. He was talking about the true transistor people absolutely hated to see that their elegant devices being messed up with all the other stuff. Essentially, these are called parasitics inside the chips. But then, and then Kilby, wrote in the lecture that he said that he didn't actually have any response to all these things because these were all essentially true statements. But as we know that integrated circuits have changed all our lives over the past 60 years. So the question really then is, what's going to happen now, right? Now that we have integrated circuits and we are facing some enormous challenges that was talked about in the previous talk. So we have this memory wall. We spend enormous time and energy trying to access data from off-chip memory. And what I would like to say is that we are hitting a miniaturization wall, which was kind of talked about in the previous presentation in terms of the Moore's law. So depending on who you talk to, we are at a 3-nanometer node or a 2-nanometer node, and we can only go so far. Now, one thing to realize is that this combination of the memory wall and the miniaturization wall is a deadly combination, because what we really did over the past 60 years is that we were waiting for these 2 years to miniaturize our transistors, so half the chip would be freed up. And what did we do with that freed up space? We put in a lot of memory. So that's why if you look at today's chips, they're dominated by on-chip memory. And the previous presentation talked about how SRAM, the static random access memory, they are not getting smaller anymore. So that's an enormous challenge. Now, one thing that a lot of people do, like when they think about alternate forms of hardware and alternate forms of computation, with this memory wall, they go and blame von Neumann. And they say that if we had a non-von Neumann architecture, somehow as if this memory wall problem would be solved. And I would like to point out that actually that's not the case, because if you built, let's say, a dedicated chip, which is a hardwired chip, for example, for a particular neural net, for example, and it was not programmable, so that's not a von Neumann machine. That's a non-von Neumann machine. But if you didn't have enough area on the chip to put all the weights, for example, on chip, so still you would need a separate memory to put the weights somewhere far from the chip, and you would have to go and spend a lot of time and energy trying to access those weights, which would be, you're hitting the memory wall, even though it's a non-von Neumann machine. So just having a non-von Neumann architecture is not somehow magically going to solve this problem. And even more interestingly, so if you read the von Neumann's, the seminal work, he actually talks about this, and he says, well, ideally, you desire an indefinitely large memory capacity, like a lot of memory, such that any particular watt would be immediately available, which kind of connects to latency and bandwidth. And he even says, how quickly, it should be at the level of an electronic multiplier, actually, he talks about in that paper. And he says, well, it's not physically possible, so we are forced into this memory hierarchy that, Professor Patterson was talking about in the previous presentation. So I say, this is the dream chip that we want to build, which is like all memory and all compute on a single chip, quickly accessible at a very low energy. Because if we would be able to do that, that would be the ultimate locality that we would have, and that would do some wonders. Now, obviously, we cannot do that, and then the question is, how can we at least try to achieve something like that, especially in the face of the memory wall and the miniaturization wall? And here comes the idea of what I call nanosystems. The point is that we have to look at technologies and beyond what we can do today. So these are the new nanotechnologies. Now, when I think about new nanotechnologies, these are not just about a new kind of a transistor or a new kind of a memory cell. It could also be a new kind of integration that we are not used to doing in today's technologies, for example. Now, with these new nanotechnologies, ultimately what we want to build are new architectures. And this is a very important point that I want to emphasize, because these new nanotechnologies must enable new architectures that are extremely difficult or almost impossible using existing technologies. Because if you just take an existing architecture, and if you just replace existing technologies with new technologies, you would be stuck by the fundamental bottlenecks of the existing architectures, and as a result, the benefits would not be very large. Now, since it costs a lot of money to invest into new nanotechnologies, that means that the benefits that these new architectures that are enabled by the new technology should better be very high, so that people would actually go and invest and get some benefits out of those things, which in turn would enable new generations of applications. For example, we are talking about AI ML today. So to recap, what did I say? What I said is that in spite of tremendous breakthroughs over the past 60 years, computing today is pretty basic. So essentially, you have a two-dimensional plane of transistors. That's what's inside a computing chip. And you actually have some wire stacks in the third dimension to connect these various transistors. So because you have a two-dimensional plane of transistors, so that's why you can only make things so much smaller, and you hit the miniaturization wall that I was talking about earlier. And then you have this memory chip, which is very far from the compute chip. And why is the memory chip very far from the compute chip? First of all, you can only hold so much on a single chip. And second, the way you build a memory chip is very different from the way that you build a compute chip. So these are various reasons why they are far from each other. And you have the memory wall. You spend a lot of time and energy going back and forth. So instead, what we are working on at Stanford is what we call is the Next 3D. NEXT stands for Nano-Engineered Computing Systems Technology. The idea is to have computation immersed in memory. So the idea is to have many layers of highly efficient logic that are deeply interleaved with many layers of dense memory. If we do that, then what do we achieve? First of all, we are no longer stuck in a two-dimensional plane. That means that, so we kind of get around the miniaturization wall. And if we can go and, put a lot of memory and a lot of logic, for example, then depending on the problem that we are trying to solve, we might be able to address the memory wall. Now, you could actually have a layer of sensors on the top, for example, to build a chip that would sense and do in situ computation and so on. But we are not going to get into sensors in this presentation. But if there was one message that I wanted you to carry home, and this was a question actually somebody asked in the last presentation, the message is about the vertical connections that are connecting these various layers. So the single most important thing over here is that what is the density of the vertical connection? So the key point is these dense 3D connections. And if we can achieve ultra-dense vertical connectivity, and I will define what I mean by density of connections, then actually we have an opportunity to achieve very large benefits. For example, to 100 to 1,000x improvement in energy delay product at the chip level. Okay? So that's a very large benefit. The question really is, how do we achieve something like this? How do we achieve these many layers of efficient logic and dense memory that are connected with ultra-dense vertical connections? So that would be a big chunk of this presentation. Now, like one thing I know that if you give somebody a lot of memory and a lot of compute on a single chip, they will only want more memory and more compute on that chip. So that's why ultimately it comes to this notion of what we call next 3D mosaic. So essentially you have a two-dimensional space. So you have these various 3D chiplets that were, chiplets were talked about in the previous presentation. And these various 3D chiplets are then packaged and assembled in such a way to build a bigger system. And this work, a lot of collaborators of mine at Stanford are involved in this work. So I would like to highlight Professor Philip Wong, who is a technologist, a device technologist, who I have been collaborating with, and I would acknowledge many other collaborators as we go through. So let's focus on this next 3D mosaic, this two-dimensional space, and we will start with the y-axis, which is this on-chip dense 3D that I was talking about, the next 3D that I was talking about earlier. And then I will come to the x-axis, which is we are going to put all these next 3D chiplets together to scale, for larger problem sizes. But one thing that I want to make you aware of is that this 3D concept is not a new idea, but mostly when people talk about 3D, they talk about something like this, that I show on the left panel. So what's going on? You have this, remember this compute chip and the memory chip that I was talking about. So somebody actually already has a two-dimensional, compute chip. And what most people talk about in 3D is that they will actually take this design, you have already decided on the architecture. And physically, when you do the physical design, when you put the transistors and wires, you fold them in the third dimension. And many people would call it 3D. Now, I call it 3D folding because what happens, as you can see, that the memory wall continues to stay over here, right? Because still you have the compute chip and the memory chip. And at best, you get some modest benefits, maybe 20, 30%, because the wire lengths have gotten smaller. And that's pretty much it. So that's not a lot of benefit to justify a lot of investment into this kind of a 3D technology. Versus what we are talking about over here is that we take this compute chip and this memory chip, and we fuse them together into this notion of this dream chip that I was talking about earlier, so that all memory and all compute are on a single chip. What this allows us to do is to create new architectural design points that would never be possible with a two-dimensional chip, otherwise. So it's not just about a physical design thing that, you have some design of a bunch of 2D chips and some 2D memories, and you just slap them on top of each other. You redefine the architecture to get even more benefits, beyond just overcoming the memory wall and the miniaturization wall. And I will show you some examples of that moving forward. But before that, as I said, the most important thing over here is that, we want ultra-dense vertical connections. Why? Because essentially we are building a skyscraper. So now think about a skyscraper where you have lots of floors with highly, populated, highly dense population. But, you forgot elevators that are connecting between the various floors of the skyscraper. That would be a useless skyscraper. So likewise, over here, the data has to move between the various layers, and that's why the ultra-dense vertical connections are very important. So let's look at how dense is dense. So what I have done over here, this is a pretty busy slide, what I have done over here is that, so remember my metric for benefits is energy times delay. It's kind of energy times execution time. If you care about throughput, it should be energy divided by throughput, for example, right? So what I have done over here is that I have looked at today's packaging, like whatever packaging technologies are available today. And then I have looked at a whole bunch of applications that are kind of written down over here. And then I said, well, if I can do this 3D technology, and what are my various choices of connecting the various layers? For the previous presentation, this point about through silicon vias came up, right? So HBM, high bandwidth memory, connected with through silicon vias. Now, the through silicon vias, it's a wonderful technology, but actually it's not that dense. In a millimeter square area, for example, you could have only roughly around a few thousand vertical connections, right? So it's still far better than what we have today, but it's not that dense. So if you have this through silicon vias with roughly around 3,000 per millimeter square, for example, that's a density, you would get some modest benefit, in energy delay product. I have written 6x. When it comes to reality, maybe the 6x will become a 2x, but still, it's a good number to start with. But if you could get 100 million per millimeter square, so that's orders of magnitude more than what you would be able to achieve with through silicon vias, essentially you have massive parallelism, massive bandwidth, and you would get roughly around 100 to 1,000x improvement in energy delay product. So what are we talking about? We are talking about multiple layers of logic and memory on top of each other, and all those layers are connected very densely. Okay? And how would you achieve something like that? The only way that you can achieve today, using today's technology, something like that, is what would be called is a monolithic three-dimensional integration. I'm skipping a lot of details. If some of you have heard about things called face-to-face bonding and things like that, you can ask me questions during the Q&A. I'm not going to get into that. But if you care about multiple layers of logic and memory that are connected in this ultra-dense way of 100 million per millimeter square, for example, monolithic 3D is the only way to do that. So what is monolithic 3D? The way chips are built is the following, as I was saying that earlier, that you have first a two-dimensional plane of transistors. You just fabricate that. And then layer a bunch of layers on top of that in 3D where you just put in metal wires. And if you have to do that, then of course those transistors have to be connected to the metal wires. There are vertical connections that are actually already existing in today's chips to do that. These are called vertical vias. And those vias, those are just vertical connections that are connecting one metal layer to another in two different layers, right? Everybody got that? Okay. So those vias are actually very dense. Those are probably the densest vertical connection structures known to humankind. Then why couldn't we do something that we take some existing chips that already have the vertical connections that are very dense, that are already 3D, and we start putting transistors and memory cells on the upper layers where we have only metal wires? Then I should be able to do achieve what I'm talking about. Now the reason you cannot do that using silicon technologies is because it takes a very high temperature to build silicon transistors, roughly around 1,000 degrees C. Now on the third layer, if you suddenly start putting silicon transistors, then all the stuff that you built underneath, all the metal wires and everything, because of the 1,000 degrees C, they would be severely damaged. So you have to be able to build transistors and memory cells at a low temperature of less than 400 degrees C. If you try to now go and put logic and memory on all these upper layers that are connected by existing vertical connections that are already very dense. Everybody got that? Now this is where comes new generations of materials. There's a whole bunch of technologies that are available now. This actually has happened over the past decade. And these are not just, as you can see, not a single technology. These are the stuff, carbon nanotubes, oxide transistors, 2D materials, and so on and so forth. People use that for logic transistors. There's a whole bunch of memory technologies, for example, ferroelectrics, magnetic RAM, resistive RAM, and so on. Those are useful for memory cells. You could even do stuff for thermal. We'll touch upon thermal and so on. So what they enable you is suddenly you can actually build these new kinds of chips with new kinds of transistors, new kinds of memory cells that you can put in 3D, and you can connect them very densely to achieve that final goal that we were talking about. So of course, I won't have the time to get into these gory details of all these materials and so on, and this is not the venue for that. I will highlight a few things to show you that this is not a pie in the sky sort of an idea, but this is actually something that's working in an actual silicon foundry as we talk about today. So I will focus on, I will pick, the carbon nanotube transistors because that's something that I work on. And I'll show you that how you can actually build interesting things out of these things. So what are carbon nanotubes? So, like all of you have used lead pencils. The tip of a lead pencil is graphite. So if you take that graphite and if you just make a sheet out of that thing, and then you start peeling things off, layer by layer, then you would be left with a single layer of that graphite, which would be called a graphene. And if you roll that graphene into a cylinder, a nanocylinder, that would become a carbon nanotube. So that's a carbon nanotube. These are nanocylinders. You can see the typical diameters are roughly somewhere around 1.5 nanometer or something like that. Well, that's not the focus of this forum. Essentially, you can use these carbon nanotubes for transistors instead of silicon transistors. And if you do that, so we actually work very closely with this organization called IMEC in Belgium. They are actually one of the big providers of R&D for the semiconductor industry. So if you look at today's technologies with silicon, people use something called a nanosheet for a silicon transistor, versus when you use carbon nanotubes to build digital systems, you have the potential for significant benefits in energy delay product right off the bat. Okay, and then there are even more stuff that you can do with it, which I won't get into the details. But if carbon nanotubes are so good, then why don't you have carbon nanotubes inside your cell phones? Well, for a very long time, it was extremely difficult to build digital systems out of carbon nanotubes because they were very unruly. They used to be very unruly, but these problems have currently been overcome. And as a result, people can build digital systems out of carbon nanotubes, mostly at mature nodes, for example, at a 90 nanometer or a 130 nanometer technology nodes. But the world of carbon nanotubes are making very good progress. I don't expect you to read this chart. I just expect you to see the yellow and the greens. So we work very closely with TSMC on this, targeting carbon nanotube transistors at very advanced nodes. So this field has been making tremendous progress. But what is really important is that is this thing called the lab to fab, which is a proverbial term in the hardware world, which says that it's okay to demonstrate certain things in a Stanford lab, for example, but do these things actually work in an actual industrial fab? So one thing that we are very proud of is that now these technologies that I'm talking about, they have undergone actual lab to fab transitions. So for example, at Analog Devices, my former student, Max Schulaker, he actually established carbon nanotubes on top of silicon CMOS, and they're building interesting products out of that. But thanks to a major DARPA program in the US, so we actually established this monolithic three-dimensional integration that I was talking about earlier, using these carbon nanotube transistors and these resistive RAM memories on top of silicon CMOS. And right now, we are actually building actual designs using those things that show true benefits of these technologies. So the key point, the key takeaway until now is that I talked about why ultra-dense 3D connections are very important. And then I talked about that using existing silicon technologies, it's very difficult to achieve these multiple layers of logic and memory with ultra-dense 3D connections. But monolithic three-dimensional integration is the only way that you can achieve something like that today. And then what I showed you is that these are things that you can actually build in actual fabs, actual silicon foundries, So there is nothing hokey pokey about these things. To show you an example of this that we are quite proud of is that this was 2 years back. Many people used to be quite skeptical about these technologies, and rightfully so, because there were lots of promises that were made in the past that were not met. So, for example, people would ask questions. Can these carbon nanotube transistors, for example, can they really drive things? Because you have to provide currents at the end. To drive logic, for example, inside digital systems, number one. Number two would be, hey, maybe can carbon nanotube transistors even match silicon? Because if you need like a 10 times bigger transistor than a silicon transistor, what's the use of using something like that? So there used to be a lot of valid criticism of these technologies. But one thing that we are very proud of, that in 2023 at Skywater Technology Foundry, which is the silicon foundry that I was talking about on the earlier slide, this is what we were able to demonstrate. That you have silicon CMOS at the bottom. Remember, that's how chips are built. Typical chips would be silicon CMOS, and then they would be just wire stacks, right? Now you have a resistive RAM in the middle, and you have a layer of these carbon nanotube transistors. Remember, that was the whole point that I was making multiple layers in 3D. And what we were able to show is that these carbon nanotube transistors driving this resistive RAM would be exactly similar to as if the silicon transistors were driving this resistive RAM. So far as a designer is concerned, if any of you are a hardware designer, I know of a few in the audience, to you it doesn't really matter that whether it's a carbon nanotube transistor or a silicon transistor. I give you something that's ISO footprint, ISO energy, ISO reliability, and so on and so forth. So you as a designer do not have to think that whether it's a carbon nanotube transistor or a silicon transistor. What you got is you got a layer of these new kinds of transistors in the 3D. Now you have to use your creativity to see that can you create interesting designs that exploit that layer of transistors, right? If you can do that, then we have won, we have gained something. If we cannot do that, then we have not gained something. I hope this is clear. And we were able to demonstrate that. And then we were able to show, now comes the next slide, that if you just, for example, if you were to go to TSMC, TSMC can give you, for example, silicon transistors and some resistive RAM memory cells on top of silicon transistor, right? And you could build AI accelerators from that. Versus now, using this technology, you would like to build different kinds of AI accelerators or different kinds of architectural design points. And can you do that? And what we were able to show is that you can, and you would get roughly around a 10x improvement in energy delay product. Essentially, what happens is that when you have RAM cells over here, a lot of transistors are used to access those RAM cells. But now those transistors have moved to the 3D, which frees up space in the bottommost layer. And since these are very parallelizable applications, so now you have more compute that you sneak in under the hood. And for the same energy, you get better throughput, roughly around a 10x throughput, for example. So this was, this is even without considering that, with more layers, you can bring in more memory and more logic and more compute, and you would get even bigger benefits. This is saying that ISO footprint, ISO memory capacity, you enable a new architecture design point because of this 3D that you could not do using this existing technology. That's a very important point to note. This is not even what I was talking about earlier, to bring the memory and bring the more compute and more memory on chip. This is even with the same amount of memory on chip and the same footprint of the chip, you get these very large benefits just with one layer of 3D. Just think about what you could do with more layers of 3D. And since I asked the gentleman if I'm being recorded and whether this will go online, and perhaps it will. So I cannot really show you what's on this slide, but you have to stay tuned. There will be a major milestone announcement that would happen around December of this year. If I were not recorded, I could have talked about this a little more. But anyway, so these are real. That's a point. All these claims that I'm making, these are not just simulation or something like that. These are real. And, and we are very happy that, this caught a lot of attention because, DARPA paid a lot of money to establish this technology. And, and so they were very happy about it. But what is even more exciting is that, as you know, that in the US, thanks to the CHIPS and Science Act, this is actually collaborative work with Berkeley. So Stanford and Berkeley together, we have established, a Pacific Northwest AI hardware hub, where, the whole idea of that is this lab to fab, this bringing these new technologies and establishing them in actual fabs and building interesting, exciting systems out of those things. So this kind of work, past the DARPA program are being heavily funded by this Microelectronics Commons. So we are very thankful about that. So I talked about technologies, and 3D and so on. So I will switch gears, and then I will spend a little time talking about systems. What kinds of systems that we can build using these technologies, and what would be the benefits of those systems, right? So, so almost at a cadence of once every year, starting from the first carbon nanotube computer, this was in 2013. Then, the first 3D NanoSystems, these were all built in the Stanford lab, right? This was not, so my students were going to the fab, they were doing the fab, they were doing the design, and they were building it. This hyperdimensional computing, this is actually collaborative work with Professor Ian Rabai over here at Berkeley. Hyperdimensional computing is it's a kind of a brain-inspired computing model different from neural nets. And we were able to demonstrate, again, using this kind of a 3D technology that, you could get some very interesting benefits. And, so, here we're talking about around 2019 timeframe, just not that far, 5-6 years back. Professor Patterson talked about all these different kinds of memory technologies, right? This RRAM and MRAM and phase change memory and so on. Interestingly, so for example, if you take this resistive RAM, which is an RRAM, it's a memory technology where instead of storing information in charge, you store information as resistance, essentially, okay? So if you looked at these memory technologies, people didn't really used to have end-to-end computing systems with that kind of a memory technology on chip on top of logic, and to show what would be the potential benefit of something like this, right? So this was actually the first published paper. This was at ISSCC 2019 that actually showed an end-to-end computing system where embedded flash, flash was talked about in the earlier presentation. Embedded flash was replaced with this resistive RAM. It's a non-volatile memory technology. And we were able to show that you would get a 10x improvement in energy efficiency compared to embedded flash if you architected the system right using these kinds of new memory technologies. When we presented this paper at ISSCC, it was well received, but there was a skepticism that, like some academic group comes and says that using this new memory technology, you would actually achieve a 10x improvement. I'm really glad that, after that publication of that paper, TSMC started working very closely with us, to create this, edge AI hardware, which, I will talk about a little bit. But in the meantime, they made a big announcement that, so Infineon, it's a major automotive chip company in Germany. So Infineon and TSMC, they are collaborating very closely to introduce this resistive RAM for automotive microcontroller products. And if you look at the announcement, it pretty much mimics that ISSCC 2019 paper. So the point is that these new technologies, they are making inroads, finally, which is very exciting. Oh, by the way, the resistive RAM that we established at Skywater in the context of this silicon CMOS resistive RAM carbon nanotubes that I was talking about for the Monolithic 3D earlier. So Skywater is actually selling, that resistive RAM, in the US, for example, as we speak. One really important point I want to make is that, like when we work on technologies or when we work on lab to fab, one single group cannot work on many technologies. But when we create designs or when we create systems, it's very important that we create new design principles that are loosely coupled with technology-specific implementations. So a lot of these claims that I'm making about the architecture level benefits or the system level benefits, they're quite agnostic to the specific technologies that we are using to demonstrate those things, because you have to use specific technologies for hardware demonstration purposes. But for a lot of these principles actually work even for other technologies. For example, if you take magnetic RAM or something like that, some of the stuff that I'm going to show you next would hold. So let's, so since I mentioned that, we have been working with TSMC on these memory technologies and how to build interesting systems out of those things. So when TSMC approached me, so we said that, okay, using this resistive RAM on top of silicon CMOS that TSMC now provides, at advanced nodes, and actually at one of the keynotes, they even mentioned that their roadmap is to provide those technologies at a 5 nanometer technology node someday. Anyway, so one of the key opportunities would be to build using non-volatile memory technologies would be what would be called edge AI, which would mean that you would have this chip that it's duty cycle, it's turned off. When you have to do an inference or something like that, it's turned on. It does its computation, goes back to sleep, so you save energy and you do a lot of computation. So I'm very thankful to my collaborators at Stanford, Professor Boris Merman and Professor Priyanka Raina. I saw that Priyanka will be speaking later this week. So we actually built 2 such edge AI chips. So the first one is called Chimera. So this was actually the first edge AI chip that would be doing both inference and incremental training. I will talk about incremental training a little bit later. And using this resistive RAM from a foundry. And this Minotaur chip is another edge AI chip. This is the Chimera was for CNNs. The Minotaur is for transformers that we published last year. Now, here is a little secret about this thing. So, all these things sound very good, the way, all this rosy picture that I'm painting. But when you actually start doing real stuff, then you see that, some things are troublesome. So I will highlight one, that came up in the context of Minotaur. So, so what is the idea? So if I can have a lot of resistive RAM in 3D on top of silicon CMOS, that would allow me to, reduce my reliance on SRAM, or static random access memory, right? And SRAM is not scaling, and it's in 2D, and so on and so forth. So, so then it would be a good idea to replace most of the SRAM with this resistive RAM, right? And it's a non-volatile, it's instant turn on, turn off. Life is great. Now, sounds very good, but at that time, now since then TSMC is making things much better, at that time, if you looked at the energy or the power for this resistive RAM versus SRAM, you would see that the power or the energy was significantly higher, 6 times more than SRAM. So if it is 6 times more energy hungry, why would you use resistive RAM, right? So you should use SRAM. Now, of course, the students dug into a lot of details, which I'm kind of skipping. But essentially, what we did was that we actually created a lot of circuit ideas to turn off this resistive RAM as much as we can, so that we do not burn a lot of power when it is not being used, right? So there is a whole bunch of, you will see all this acronyms over here: clock gating, macro shutdown, full shutdown. The hardware designer types, these are they would connect to these things anyway. So what this allows you to do now is that while the chip is running inferences, for example, it's not that your demands for bandwidth is always the same. So for example, over here you see that if you look at some neural nets, so the amount of bandwidth that you need would vary from layer to layer, which means that you can go and you can do this dynamic optimization of energy versus bandwidth, because now you can turn things on and off dynamically while the system is running, which means that now you have to get into compilation, and when your design is mapped, you have to kind of decide that what you would turn on, what you would turn off. And if you can keep doing that, then you are always at this kind of this near optimal operating point with respect to both energy and bandwidth. And we were able to show some of those ideas in actual hardware, as shown on this chart. And now you see that suddenly, so I was talking about technologies, and then I was talking about hardware, and then now compilation and software starts coming into play, because now we have to dynamically manage all these resources while the system is running. I will go one level up, and this is something that many people call co-design in our lingo. So I will give you another example of co-design. So when like TSMC approached me, this was in around 2019 timeframe, and we were going to build the Chimera chip. So I said that using Chimera, we would do not only just inferences, but we should also do what used to be called incremental training at that time. Now it's called fine tuning, which means that you have the neural net, and then you tune the weights of the neural net, and people were rolling their eyes. And that's because, if you look at some of these memory technologies, such as resistive RAM, they have this challenge which is called write endurance, which means that you can only write so many times into a memory cell. If you write more than that threshold value, your memory cell will die. Okay? And then people said, well, but if you try to run stochastic gradient descent, then this chip will just survive for 2 weeks, even if you ran 20 images per second. Okay? That's not acceptable. You want 10 years. And so our response was, well, that's because when you do stochastic gradient descent, the conventional way, nobody have given the computer scientists the constraint that writes are more expensive than reads. Right? So, by the way, for resistive RAM, this is a reliability issue. But for a lot of these non-volatile memory technologies, writes are generally more expensive than reads, even from the standpoint of energy. So then the question is, if this constraint propagated to the higher level, to the algorithms level, that writes are more expensive than reads, then what would you do? And remember, this was around 2019. There was no LoRa at that time. And so Albert, who was a student of Boris Merman, he came up with this idea called low-rank training. And that's sort of what we implemented on this chip. What that did was it reduced the number of resistive RAM weight updates steps by 100x. We were doing more computation, so we were spending computation energy, but we were having fewer writes. And as a result, this is measured data. The energy delay product was 340x better than running stochastic gradient descent. And obviously, we could go up to 10 years at 20 images per second. So I think this is an example of this co-design, and perhaps one of the reasons for a workshop like this. So what are the constraints, for example, we could propagate to the higher level, so that like we could do better things. Yeah, you had a quick question? Yeah.
So as someone who has worked on databases and files, algorithmic side, databases and file systems and so on, and taken the data structures all the way to
Right.
the systems, I talk to people about this wear-out issue, and as far as I can tell, on even numbered years, they tell me it's the most important problem, and on odd numbered years, they told me it's not a problem at all in any paper I wrote on that topic.
Okay, well, it seems like I might spend the rest of my talk, we can talk about it during the break.
Okay.
Yeah, but thank you very much. Yeah, okay. But this is a real problem, depending on what memory technology you're using.
It's 2025,
Yeah.
so it's a real problem.
It is a problem, yeah. Okay, I would like to highlight another example, right? Now, I think these issues would be even bigger moving forward, which is like, I talked about two kinds of memories, like SRAM, which is like very good, but you cannot have a lot of it. And then I talked about resistive RAM, which has very good retention, but it has very bad endurance, for example, right? By the way, Flash has worse endurance than that. But there could be other memory technologies. For example, here is this new memory technology idea that people are pursuing, which is called oxide gain cells. These memory technologies have very good endurance. They're extremely good. You can write as many times as you want, but they do not have a very good retention, which means that now, the question really is, can you think about your data structures where you may not have to keep your, memory doesn't have to store things for very long. Maybe a millisecond is like infinity for them. And by the way, those memory technologies can also be integrated in this 3D that I was talking about. And this is something that we are working on. This was the first paper that talked about it. So again, I think that technology space, the richness of the hybrid memory technology space is opening up. And that requires, I think, a lot of interactions with the algorithm designers and the technology folks. Now, this used to be difficult in the old days when we had general purpose processors. So what are we going to do? We have to satisfy everybody's needs. But now that we are in the region of these domain-specific accelerators, I think that creates opportunities to explore that synergy. Anyway, so I actually have, I think, another 10 minutes. So, 10 or 15 minutes. So I would, switch gears. So I talked a lot about the y-axis. And now I will spend a little time talking about the x-axis, which is, remember, this idea was we have these 3D chiplets, and we have to put many of these 3D chiplets, because if you give somebody a lot of memory and a lot of compute, they will need even more memory and more compute, right? So let's go back to our definition of the dream chip. And let's say that we need n times m amount of memory, and you will see why I kind of broke it up into n times m. And the idea of the dream chip was that the full workload fits in the on-chip memory and on-chip compute, for example, right? And we already said that this is infeasible from the get-go because it's a moving target. So what are we going to do about it, right? So let's say that I can have only m amount of memory, per chip, for example, right? So one thing that I could do is that I could have a large off-chip memory. And even if I use HBM, this is not going to be anywhere close to the dream chip that I was talking about earlier. So you hit the memory wall, right? And so clearly I'm not going to do something like this. So can we do something else? Now we go back to essentially the idea of multi-chip parallel systems. So essentially, now you see that instead of having this n minus 1 times m amount of memory, I have n chiplets where each chiplet has m amount of memory, and compute and buffers and so on and so forth. Now, if we take a step back and look at this picture, and this is something I called an illusion system. If you take a step back and look at it, and you would say, what is this guy talking about, right? This is known since the early days of computing. ILIAC 4, which was in the 1960s, used to look something like this. So, am I just giving a new name to something that exists? And the answer is no. The point over here is that here what we are trying to do is we are trying to create locality in the following way. First of all, you do not need all memory and all compute on a single chip. What you need is enough memory and enough compute on a single chip, right? So obviously, if I have only 1 bit of memory on chip, then I would spend all my time and energy accessing memories that are on other chips. But if I have a sufficient amount of memory and compute on a single chip, then I might have a good starting point to start with, right? So now the question is, what is this enough on-chip memory, for example? Well, we are in the world of domain-specific accelerators. So depending on the domain that you are working on, you can derive what this enough is. So now let's say that you start with enough memory and enough compute on chip. But remember that these are highly parallelizable applications. So if you take, for example, a typical parallel computing mapping that most people use, right? There's been a lot of work by people in this room and others, on mapping on parallel processing systems. So if you just indiscriminately parallelize, your application, then what would happen is that you would have a lot of things that would be running on a lot of these other chips, but they would be spending a lot of energy going back and forth between these various chiplets, right, or these various chips, which means that even if you could parallelize your application, you should not parallelize to the to the best level, because you would be spending a lot of energy in the traffic. Now, guess what? So if you're now not that greedy, so you say, well, I hold back and I'm not parallelizing as much as I could parallelize, which means that some of these chiplets some parts of these chiplets would be idling. Make sense? Because I could parallelize, but I did not parallelize, so I didn't assign my jobs over there, which means that one thing we didn't quite talk about in the earlier presentation is that, remember there was this talk about Dennard scaling and all that kind of stuff? That has to do with the leakage of the transistors, the leakage power of the transistors. So if transistors are sitting idle, they're actually going to leak. And that's going to consume energy. So you do not want something like that. But guess what? Remember I was talking about this quick and fine-grained turning things on and off in the previous part of my talk, right? When I was talking about this RRAM and SRAM and things like that. Those ideas hold for all these memory technologies. So which means that now, if you start with enough memory and enough compute on chip, and then you have this thing about quickly turning things on and off, then actually you create special kinds of mappings that would otherwise not be possible with just plain and simple parallel processing mappings. And you can actually achieve your overall energy delay product within 10% of the dream chip that you could not build. So that's why we call it an illusion system, because we are trying to create an illusion of the dream chip using these multi-chip systems, and that achieves close to this very large energy delay product benefits because we are very close to the dream chip. Obviously, we are not going to be the dream chip because we have to still spend some time and energy going back and forth. But the key points are this enough memory and enough compute per chip, and this quickly turning things on and off. This combo actually allows you to do something like this. So we actually have built these illusion systems, multiple generations of illusion systems hardware. Yeah?
When you turn off, does the data go?
No, the data stays there because of the non-volatility, right?
I see,
yeah.
Okay.
But even if you had a volatile memory, so I'm taking an extreme where I'm completely turning things off. But for example, if you have even a volatile memory, there are many opportunities. These are called various power-saving modes. So even if you do not completely turn it off, you still have a very little energy, for example. Yeah. So there are various levels that are possible. Yeah?
So because writing is more expensive than reading,
yes.
I assume I wouldn't want to parallelize a matrix multiply, say, over all of this.
Yeah, you have to be very careful about that. Absolutely, yes. So again, to show what I was talking about, I already covered this thing. So we talked about chiplets in the previous presentation, right? And what the industry is saying is that we want chiplets and chiplets and more chiplets. And I think somebody from over here, brought up this point that, but if you have chiplets, then like the inter-chiplet energy is just going to kill you. And that's exactly the point that we are making, right? So just indiscriminate chipletization is not going to save us, right? And at the same time, even if we limit parallelism, the idle energy would dominate, and that would kill us. That means that we have to, have the special kinds of mapping, have to solve this problem, which we did. I will spend 2 slides on that in 2 slides. But what this shows is that now, remember this Minotaur chip that we were talking about? And we had 12 megabytes of on-chip resistive RAM that TSMC gave us. We wanted to run a mobile BART of 96 megabytes, and we do it in the illusion way. And what this is showing is that as you scale the number of chips, you retain that illusion. That's the point being made. And there has been some interesting work. For example, NVIDIA published a paper called Simba, which was, again, a parallel processing mapping on chiplets, for example. And you would see that you would get an order of magnitude improvement compared to that parallel processing mapping when you do this illusion. Now, what do we do? How do we do this illusion? Well, so my former student, Robert Radway, he actually came up with an MIQP formulation for to understand all the constraints. And of course, we had to do a lot of work to make this thing run in a scalable way for very large AI models. So you can see that what would otherwise take hours to run, we can actually run that in seconds. And so anyway, so that's our way of you provide a PyTorch model, for example, and you have these chiplets, and you have all the characteristics of the the interconnects, how much memory per chiplet, and so on and so forth. How long does it take to turn things on, turn things off, and we can come up with actual mappings and schedules that achieve illusion. So as I was saying, there are lots of papers that have been published, by people, again, and compared to that, you can see that we achieve quite a few interesting results, versus those. So I have at this point another 6 minutes left. So what I'm going to do, I could go on and on and on talking about other topics because this never ends. For example, you could ask the question, as workloads grow, can you keep doing illusion? I can spend time talking about that. 3D, when you think of 3D, you have to worry about thermal. What is the cost aspect of all this? Yield and repair, so on and so forth. So of course, I'm not going to spend time talking about all this. I will take a little time talking about this 3D thermal and the cost, and I'll be out of here. And I'll answer questions, and we'll have a good 10, 12 minutes. So when you do 3D, the first thing that people worry about is how to get the heat out. Now, in the first generation of our 3D chips that we are building, what you have on the upper layers are the memory and memory access circuits. So memories are generally cold. And that's why thermal is not a big problem. But when you hit the miniaturization wall, ultimately, you would want heavy-duty AI accelerators that are running on 3D. And when you try to do that, extracting that heat out is the significant challenge. And the question is, how the heck can you get the heat out? Now, when people think of heat, the first thing they think about is the heat sink. That, do I have a big enough heat sink to sink all the heat, which is, of course, very important. But as shown over here in this pie chart, when you talk about a 3D technology, actually the real problem is not just the heat sink, but actually the trapped heat. You have like this heavy-duty compute that's running on the 10th floor or whatever, and that's generating a lot of heat. But actually, you do not have a lot of conduction from there to the bottommost layer or wherever your heat sink is. And that is actually this trapped heat is a major problem. Now, why is trapped heat a major problem? I'll go back to technology a little bit again, okay? So again, remember that chips have many layers, right? We are talking about, right? Even with metal, and these layers are, they have insulators between the various layers, right? Otherwise, there would be a giant short inside the chip. Now, those insulators have very low dielectric constant because you want fast chips with low energy, and the capacitance is related to the dielectric constant. Now, unfortunately, all those insulators are also very bad conductors of heat. And as a result, the trapped heat, it's not easy for the trapped heat to travel to the heat sink. Now, one thing you could do is that you could say that, oh, don't I have a lot of vertical connections? So I add a lot of vertical connections. Those would be like chimneys or heat pipes. That would bring the heat down to the heat sink. Yes, you could do that, but then the size of your chip is going to blow up. So you cannot quite do that. So what would you do? So, so one of my colleagues, Professor Shrabanti Chowdhury, so when she joined Stanford, we were talking, and I asked her, I said, can you actually give me a dielectric which has a very good dielectric constant, but at the same time, it's a very good conductor of heat. Now, Shrabanti actually works on polycrystalline diamond, and she has made some breakthroughs in that space. Now, polycrystalline diamond has very good conductivity, thermal conductivity, and it has a moderate dielectric constant. So what we are doing right now is that when we design chips, when we are building chips, we want some of these dielectrics to be the existing dielectrics that have very low dielectric constant. That's very important from an energy and a speed standpoint. But some of these dielectric layers are this thermal dielectric using polycrystalline diamond that Shrabanti is creating so that we can spread the heat at certain points and then use very few heat pipes to just bring it down. And when you do that, you see over here that you have a significant improvement in the number of 3D layers that you can satisfy. Your peak temperature goes down significantly, and you don't have to pay a lot of area price to be able to get your heat to the heat sink. Okay, and and then the last topic, well, that itself would be worth of several hours of a seminar, would be to talk about cost. So like we were talking about cost per transistor and all that kind of stuff in the previous presentation. Now, while cost per transistor is a very important metric, one of the points I would like to make is that that was actually a driving factor, I would say, in the 20th century when people in like companies like Intel would take 4 years with an army of design team of 1,000 engineers to design a microprocessor, and then they would sell 1 million copies of that microprocessor per chip. So the design cost gets amortized out, and what you're left with is manufacturing cost, and the cost per transistor is a very dominant metric. Versus now, if you look at what's going on with hardware accelerators, is that you want to design these hardware accelerators very quickly, very cheaply, using a very small design team, right? Which means that the design cost must go down very significantly. And if you look at design cost is dominated by design verification cost, which means that when we think about building domain-specific accelerators using this, especially these new technologies, we must solve the design verification problem. And existing ways of doing hardware design verification lack solid technical foundations. So that's on the design side. And now let me tell you something about the manufacturing side. So today, for example, when for example, data centers, they buy lots of chips from various vendors. And so when they buy chips, the expectation is that roughly around, if somebody bought 1 million chips, roughly between 100 to 500 out of those million chips would be defective. And they would do something about it. That's what the expectation is for the commercial. Versus if you look at what's happening in the data centers today, is that things are off by at least an order of magnitude. They are seeing 5,000 defective chips per million in the data center. And a significant chunk of those defective chips, what they're doing is they're causing what is called silent data corruption, which means that if you had a defective chip and your system was always crashing, that it's not very pleasant, but it's OK. But a significant chunk of these defective chips, they are actually producing erroneous results without anybody knowing that the results are erroneous. These are the most insidious kind of problems that can happen. And this is a major issue. So there are papers by Google and Meta and others that I would encourage you to read. Like talking about CS problems to solve, this is actually a major issue that I think moving forward, since we're talking about emerging technologies and things like that, this is a major, major big deal. I won't spend much time on this in the rest of my presentation. Instead, I would spend a little time talking about design verification. So as I said, that one needs to be able to do design very quickly using a small design team to be able to build accelerators using these new technologies, because that's going to be the future. Now, when you do that, how are you going to do design verification? As I said, that existing ways of doing simulation for hardware design verification, it doesn't have any thoroughness guarantees. And even formal verification, existing formal verification for hardware, it doesn't scale for very large designs. And still, you have to write these properties that you're trying to verify. And those properties are, nobody knows how good those properties are. Your verification is as good as your properties. So at Stanford, we have created this new approach called GQED. It stands for Generalized Quick Error Detection. It's a new kind of a formal verification where you do not have to write any properties or assertions or anything like that. What you have to do is that you have to provide the design. You have to provide what we call is a command view, which is like an instruction set architecture if you were talking about a programmable system. And you have to provide the interface through which this accelerator is going to communicate with the rest of the system. And this is the only thing that you provide. You don't have to write any assertions or any properties or anything like that. And GQED would do the verification for you. And it is the only technique that's known that finds all bugs up to the bound that a bounded model checker can run. It's very scalable. It runs for 250 million logic gates. We have actually done that already for bugs that are 300,000 cycles deep. To give you a perspective, if you actually try to run a 250 million gate design using 2 days verification, the tools would crash. It would not run. This approach doesn't have any false fails, and it provides drastic productivity benefits. So we actually applied this technique at several companies now. And we even found chip killer bugs, or even bugs that are like very critical bugs that conventional verification flows did not find. And these are at major companies, as you can see. And even at places where formal verification is widely used. And from a productivity standpoint, it's highly productive because instead of spending a year of verification, you can accomplish that in 3 weeks. Why is this important from a design standpoint? Is because now you can actually use AI, generative AI, to do design. If you try to use generative AI to do hardware design today, you are stuck by design verification and design bugs. But because we have this new way of doing design verification that also allows you to do localization and generating hints for bug fixes, now actually Gen AI can actually create the design. And we actually have run very big designs. And we see very large improvements in productivity at very low cost. So this is where I would end my presentation. So to conclude, the next 3D MOSAIC idea that I was talking about, it breaks a lab to fab glass ceiling. like people always used to say that people work on all these new technologies, but are these going to have any real impact on anything? To do that, first of all, you have to establish them in industry fabs and foundries, which I kind of talked about is happening right now. But what is even more exciting is that people are trying to create interesting products out of these things. So these are not just some academic pursuits. The second point is what I talked about provides large end-to-end benefits, not only just at the 3D chip level, but creating this illusion system using these multiple 3D chips. Co-design of the right kind is very important. Co-design of the wrong kind could be dangerous. But there are opportunities for combining these device technologies and 3D and connecting them all the way to software and algorithms. And the last point is that when we are talking about emerging technologies and compute using emerging technologies, I think design productivity and robustness has to be extremely important. And this is where this GQED and the ABCD, this AI-boosted chip design that I briefly mentioned would be very important. So thank you for your attention, and I'll be glad to take questions.
Other innovative designs like photonics chips or?
Yeah, so I'm being recorded, so I do not want to make too many comments about photonics chips. There are two kinds of things that people talk about for photonics chips. One is what Professor Horowitz and Professor Patterson were talking about, where you are using photonics for interconnects, okay, right? And Professor Horowitz gave a very good overview of this co-packaged optics and all that stuff. Now there is another idea that's floating around, which is about using the photonics to do the computation itself. And they come in various shapes and forms. There have been some early work on using AI, and then there was a paper that got out of Microsoft last week, I think, or 2 weeks back in Nature. So I think the real question is, what are you trying to achieve? And ultimately, what is the end-to-end benefit of something like that? That needs to be computed. That's where I would leave for the public part of my response. Okay.
I remember like a long, long time ago when I took a VLSI class, we had a layer of wires that weren't made out of metal, polysilicon. And those, I think, would have been resistant to high temperature fab.
But nobody uses this polysilicon anymore.
But
yeah.
could you do that for your vias, through your vias?
No, the vias are already metal vias, actually. If you use polysilicon for your vias, then those vias would be so bad that they're not going to be good. But this is not a problem anymore, as I said, that because of the low temperature fabrication. Yeah.
In your more topics slide, you had computing inside the memory array.
Oh, okay. Yes, I intentionally put that. So if you look at the list of the topics, there was something about a topic that I'm passionate about, which is I am passionate about arguing about, let's say, which is computation inside memory arrays. So there is this idea that you could use the physical properties of the devices themselves to do computation. Now it comes in various shapes and forms. Shahar, who I know very well, he has one way of doing it. Now, I haven't studied that specific one, very carefully, so I'm not going to comment on that. And in any event, you're going to talk about it, right, on Thursday or something like that, and we can have a discussion about that. Now, there is another kind, and I don't think you do that kind, which is, remember that we are talking about this resistive memory and resistances and things like that. So if you have a resistance, and if you could program that resistance, for example, then essentially, you could actually, try to solve Karpov's laws, right? Because you have I and R, essentially, right? So then, if you have a matrix multiplication, then you could, solve matrix multiplication in an analog way using, these resistive memories, right? So, there are a lot of people that talk about an implementation like that, and many people I call it computation inside memory arrays to distinguish from what I'm doing, which is computation right outside memory arrays, okay? Anyway, so the challenges with that specific approach, so I'm talking about that specific kind of computation inside memory arrays, is that first of all, the memory well continues to stay there anyway, right? So, if you have, if you do not have a lot of memory, then like you can only do so much computation, even if you try to do computation inside memory arrays. That's the first point about that, which a lot of papers do not talk about in that domain. The second issue is that when you have this computation inside memory arrays using analog computing, still you have to digitize those things and get it out and then do some rest of the computing there. And one needs to pay a lot of attention to the energy, for example, of these converters, from the analog to digital converters, for example. Now, the third point, which I think is a bigger point, is that oftentimes people do not, people just talk about, well, somehow magically they would be taking a very large memory array and they would be doing this computation inside that memory array. Now, if you have a very large memory array, that is quite an energy inefficient memory array to start with. Nobody builds one single giant memory array. People build many small memory sub-arrays from an energy efficiency and area efficiency standpoint. Now, if you try to do something like that, then what one needs to then take into account is that you have this intermediate results that are coming out of your memory sub-arrays. And then you would need some kind of a digital block or something like that to combine those results to get your final results. And that's where Amdahl's law would be very important to see where your energy goes then. So I think, for those kinds of approaches, I think a true end-to-end analysis is absolutely essential. And I have not seen many publications that actually get into those details. You work on this, Sharon. Would you agree with me, my assessment?
Very good points.
Okay.
They're all good points. Could I follow that?
Sure.
With actually your second point about end-to-end benefits. When you analyze the end-to-end benefits, the numbers look really good. Now, is it possible to actually isolate which layer are these benefits from?
Yes. So we do that. So if you look at some of our papers, for example, when I claim that why vertical ultra-dense vertical connections are very important, yes, we tease out that how much is coming from the vertical connections itself. If you had a more energy efficient logic, for example, on top of those vertical connections, then what would be your incremental benefit for that? Yes, we try to do that. Yes.
So then at the end of the day, based on, let's say, for your MOSAIC or this Miniature, I think you call it, the type of system, where do you see the most gain coming from?
So, you try to keep as much as you can on chip, and with dense connections, that is the first most important thing, which goes to locality, essentially, right? You want to keep things as local as possible. And when you cannot do that because of various constraints, for example, for Minotaur, it was because TSMC gave us a certain chip size and certain amount of memory. That's where you try to do all this illusion stuff to almost fake that as if you are trying to be as local as possible. So these are kind of the two big knobs, I would say.
So the technology, the bottom part of technology, how much does that contribute? Let's say if you use RAM versus you use FerroFETs.
There would be some benefits fundamentally from the, so for example, if technology X was better than technology Y by a certain amount, that would get reflected because ultimately when you have the dream chip, then you are compute bound, right? Because it's almost like all compute and all memory, and that's when, yes, technology will play a role. But before you get there, if you didn't have a lot of good vertical connections, for example, then, or if your chiplets were connected with, very energy-hungry links, then it doesn't really matter how much benefit you brought at the technology level for, replacing one memory kind with another. That would not be reflected at the system level.
Okay, I have a question that you mentioned that there is a design your system that turn on or off your chips, but I design parallel algorithms, and what we are basically trying to do is to make sure that every chip is working at its best.
Right,
so
and
it's kind of a conflict.
That's exactly right, and that's a point I'm trying to make, and I think that is something that's going to be important. And the reason for that is especially when you care about energy. If you did not care about energy, if you just cared about throughput, you could be okay, because you could pre-schedule and things like that, so that especially for this neural net kind of workloads, you send it, schedule it so that it's sent and it's there when it's needed. But as soon as you care about energy, which you do, then energy you cannot hide, right? Because it's an additive factor. So yes, so even if you could make use of a lot of parallelism, you should not use, you should use balanced parallel. Maybe, we should come up with a term. You should use balanced parallelism because you do not want to have that traffic kill your energy. And so now you see exactly, so then it's a trade-off that starts coming in. Because if you do not make use of that thing, as I was saying earlier, then that's going to sit idle, and that's going to consume leakage energy, and which you do not want either. So that's why a giant optimization is very important.
So I see. So I think the idea is that when your parallelism cannot work and make use of the full chip efficiently,
that's when that's exactly right. Yes, exactly.
I see. Thank you.
Yeah.
So does that also say a bit about you mentioned the solver
Yeah.
that somebody that had presented.
Right. Exactly.
For scheduling, what was it, AI
That's right.
computations or
Yeah.
something?
Yeah. Exactly.
Can you say a little bit more about it? So
Yeah. So the solver that we are using Gurabi at the core, but so my students spend a lot of time trying to write the constraints right, and this is like a total messy set of constraints. Because what we have been trying to do is, we are trying to look at the whole space, like what Sharon was, asking earlier. So it's not just, you have this much amount of memory, and this is your quality of your links, and then, what kind of mapping you would get. But if I had a spectrum of links, for example, with various capabilities, right? If I had a spectrum of certain kinds of memories that have a certain trade-off of, amount of density or amount of capacity versus, their energy of accesses and things like that, can I look at that whole space? And so, so we represent all that, and then, as constraints, and then try to solve. And obviously, as you can guess, that if you try to, and we are doing MIQP, so it's, because we have energy and throughput, right? So it blows up very easily. And then we have to be, careful about what are the tricks that we pull so that, we can get good numbers without spending, hours and days. Yes. So, but I'm happy to get into, deep details. Yeah.
One more question. So it's a bit more fundamental. So you have a 3D design with layers. What is the limitation of putting those layers in 2D so it's easier to manufacture? Like,
right. Thank you very much. Actually, I actually had that on my list. I call it rapid fabrication. So I'm really glad that people are asking this question. So let me try to rephrase your question and see whether I got it right. Okay, if not, just tell me. So what I'm doing is that I'm taking this one layer and another layer and the third layer and fourth layer, and I'm doing it sequentially, one after another. And one of the drawbacks of that sequential approach is that it could take a lot of time to fabricate a chip, right? Another drawback is that if one of those layers, for example, was defective, then my whole chip is defective, right? So these are kind of two big problems. Instead, you could try to do the following. You could just build all those layers separately and then somehow magically glue them on top of each other. Then first of all, you could, if those layers could be built in parallel, you could think of a binary tree of assembling those layers, for example, right? For example, and you could test those layers, ahead of time and then put them together, so that would improve yield. Is that kind of the question that you are trying to ask?
Not really.
Okay.
I was more comparing to just having it, like, for example, you have 12 layers.
Yeah.
So you just have them on the chip, and instead of connecting up and down, you
Okay. So by the way, by the way, okay, so, remember in the previous presentation, Professor Patterson was talking about reticles and, like how, like you have reticle limited chips and so on. By the way, there's a company called Cerebras that's actually building, wafer scale chips basically, right? Yeah. But again, you are going to be limited by, like whatever, your wafer size is. Beyond that, you cannot go, number one, like whatever your real estate size is, number one. Number two is, if you have those, things side by side, then depending on how many pins you got or how many IOs you got between these various, microchiplets, let's call it, for a lack of a better term, you would be limited, so far as the bandwidth is concerned, you would be limited by those connections, right? So those are the fundamental bottlenecks that you would face, no matter what you try to do. Yeah.
In the examples that you showed, you still kept the traditional
silicon
transistors
CMOS. Yeah.
At the bottom layer, and then the additional transistors were used to drive these memory chips. Is that something that you see as like the primary way that
No.
will go forward?
Yeah, thank you for asking that. No, that is not our goal, right? Ultimately, I would want, like just, full compute on all these various layers and so on. But if you work with any kind of this lab to fab kind of a situation, it's not easy to do that, right? So that's why it's very important to think of demonstrators that would show the benefits of a technology without having to do the whole thing and then convince people that if I could get this much benefits just by doing this, then I could get even more benefits by doing a little more. And that's how this world works. And that's why our journey looks like that. Yes. So we are at that level where we can put N-type and P-type transistors on the upper layers, right? So we can actually do those things, in the foundry, for example. But as I said, that it takes a lot of effort, to actually make things work. And so far as end-to-end system demonstrators are concerned, we are demonstrating those things right now while we are working on more sophisticated demonstrations.
You don't see it as like a...
It's not a showstopper, yeah. There is nothing fundamental that would stop us from doing more. It's a matter of how much time and energy and money and effort we are putting in.
So just a little bit about the schedule. So we have a long lunch break. We'll be back at 2:30.